Hello everyone and welcome to today's webinar where we're going to be discussing differential model building in MASTA. The reason for today's webinar is just to discuss the slight differences in modeling a differential system over the standard model building processes in MASTA. We do have a few questions come in about this modeling process. It does have a few different nuances, a few slightly more difficult aspects to it than your standard modeling process. So the webinar today will be a maximum of 1 hour long. It's likely to be a little bit shorter than this based on what we've got to go through, but there should be plenty of time for any additional questions if anyone has anything to mention. If you do have any questions, please feel free to ask them in the questions panel on your GoToWebinar window. I will try and address them as we're going through the session or at the end of the session. If I don't respond to them during the webinar today, then I'll reply to you after the session is concluded. We'll follow up on all of your queries. There will also be an available recording of this webinar, so if you do need to review it at any point, so while you're building your own differential unit, then it will be uploaded to our Wistia account shortly upon the conclusion of, well, after the conclusion of the webinar. And the link will be distributed to everyone who's attended today, so you'll be able to access it. Right, so this is what we're going to be building today, or let's say a simplified version of this. And we're not going to focus much on the actual modeling of components and modeling processes. It's more the layout of the components that are necessary for our differential unit in order to get it to function. So just as a reference, this is what we're going for. We have the differential housing here, and then contained within it we have a differential pin shaft, which contains our planet gears. We have a bevel differential gear set to our left and right half shafts, which are where our outputs sit. Now the reason we need a specific video for this is generally these components around here. So there is some confusion as to why exactly we need this configuration and what we do to actually model some of these components. Now obviously I'll go through this in more detail as we progress through modeling our own system, but the main ones I want to bring your attention to here are the bearings here, which are sort of scattered around the differential model, and this small shaft section here, which is highlighted at the bottom, which we're calling our stub shaft. Now starting with the clearance bearings we have here, these are, as the name suggests, they are just to model any clearances in the model, and they allow us to fully constrain the system as it would be in reality. So it's, for someone who's not sort of a very well versed in creating master models, it can sometimes be a little confusing as to why these are necessary. But having these components and having one side connected to here and the other side connected to here ensures that MASTA knows that there's a potential connection point between those two components. So the user can define the actual value of the clearance on this component here. So let's say it's 20 microns, for example. And then when we actually subject the system to load and it deforms, if that component moves, or this component moves by over 20 microns, then it starts transferring load between those two components. So in order to fully constrain our system in a realistic way, we'll often need some of these components. And these are axial clearance bearings, just to reiterate. We also have several radial clearance bearings in here as well. They don't necessarily need to be clearance bearings, they could be just concept bearings. But again, they're just in there to apply clearances or define clearances in our model. The other general point of confusion comes around, as I mentioned, with this stub shaft here. Now, the main reason we need this, if I just wait for that to rotate slightly and stop it there. So this whole assembly here is hopefully quite clearly representing this pin connection assembly there. So we have this blue component, which a lot of you will recognize from planetary gear sets. So that in a planetary gear set, it's a planet carrier component. In here, it's a differential carrier component. And what that is essentially doing is allowing us to change the modeling orientation. So for one, it's telling us that it's expecting some differential planets to be in there. So it's going to revolve that whole assembly X amount of times based on your number of planets. But it's also suggesting that we are changing the orientation of modeling. So from our differential housing, where we're modeling in this direction, so from left to right on my current screen, if we go through this blue component here, this differential carrier component, that switches the orientation of modeling. So the differential pin is actually being modeled from top to bottom on my current screen configuration. So this component changes that orientation. The reason we need this stub shaft component here is in combination with these clearance bearings. So basically, this clearance bearing here is intended to allow us to model any contact between the planet hub here and the actual differential casing itself. So if I had the axial clearance bearing connected to just the differential planet hub here, that's fine. But then it wouldn't be able to connect directly to the differential housing on the other side because it's in that opposite orientation. So the reason for this stub shaft here is so that we can still have something to connect the other side of that clearance bearing connection to. So the stub shaft is modelled in the same orientation as the internal assembly, which if I click on this button here, it will orientate it to that direction. So the stub shaft, which can be fairly hard to select on occasion, okay, so the stub shaft there is modelled in the same orientation as the internal units, and that allows us, so you can see this is an axial clearance bearing, which kind of gives that away. If it was modelled in the other orientation, it would be a radial clearance bearing. That allows us to model the connection between this component on the left and the stub shaft component over on the right. So we can get an accurate representation of clearance between those components, and if it moves enough to transfer load, we'll capture that information. And then the stub shaft, really it's just a concept component. In reality, it is not part of the actual system. It is just an aid to our modeling process. So connected to our stub shaft is the blue component, so the differential carrier. And then on the other side of the differential carrier, where it flips the orientation, is the actual carrier shaft. Now the reason we can have this stub shaft component on here fairly safely is because it's not actually going to be there in our finalized model. When we're modeling something like a differential housing, there's a good chance it's going to be radially asymmetric. So something like the big holes cut out in the side here so you can reach the internals. And if you have something like this, it's a component that you would be replacing with a FE component. So like I have done in the model image over on the right hand side. And what we can do is replace both the carrier shaft itself and the stub shaft with a single piece of FE component. So that basically means that both of those components are overridden by this one piece of FE. So the fact that there is this additional piece of shaft around our master model doesn't matter, because it's no longer, it's holding the model together, but it's no longer being considered in terms of sort of stiffness and additional mass that it provides. That's all now being controlled by the FE component. So hopefully that describes why we need this component, and when we actually go through to start building this, it should make a little bit more sense as to why we are doing it. Okay, so I'm going to start here. So this is a blank model. All I have is a reference guide. You don't necessarily need this. I'm just using it for ease of use in this particular demonstration. It's a 2D DXF, which is in the background of my model. And I'm going to use this as an assistant to create my differential unit. So, start off just by creating a shaft profile. The purpose of this webinar is not to go through the complete modeling process, so how to create a shaft, how to connect things. So I'll do much of this fairly rapidly and then focus on specific parts. So if you do want to know how to do these types of modeling in more detail, there are videos to do those. But the first thing I'm going to do is link my DXF to the background of this shaft so I can use it as a guide for my modeling process. So I'll say it uses CAD guide, pick a reference, and then align that reference. Okay, and with that reference aligned, I can model that differential housing shape. You don't need to worry about the radial asymmetry, because just to reiterate, in a differential, it's a prime candidate for replacing the differential shaft, differential casing, with an FE component due to that radial asymmetry. So that's our outer profile generated. I might just stretch up to this section as well, just to make it nice and simple for us. And the inner profile. Okay. Next, we'll add a couple of bearings onto here, just to keep it nice and simple. I'll just add concept bearings in the place of these here. Okay, and now I'm going to add a power load, which is going to represent my input power load into this system. Now, of course, in reality, we probably have a gear set on here. But for now, I'm just going to represent the input of the system in this location. Okay, so to start with the internals now. So we remember from the completed model that from the differential housing itself, and I can see the connections in my design mode here in this list at the bottom, I can see that it has a connection directly to our differential planet carrier component. So this is what we're going to add and connect to our differential carrier. And then to the other side of the differential planet carrier component, the blue component, we'll have that stub shaft component, which, just to remind you, is kind of a placeholder only. It's not going to be represented in the complete and final system. So if I go to the Add Component list, Gear Sets and Differentials, and then there's a component here which is the Bevel Differential Planet Carrier. I can connect that to my casing. And then there's a few different settings available on here, very similar to the ones you might find on the similar component for a planetary gear set. So for example, I can control the first planet angle, the number of planets, if I've got more than 2 differential planets, and the planet diameter, which is what I'm going to play around with now, just to generally get it sat at around this diameter here, where the connection point is going to be between the pin and the housing. So 90 will do as an estimate. Okay, and then to the other side of my planet carrier component, as I mentioned, is going to be our stub shaft. So I'll just drag and drop a new shaft shape. Stub shaft. And you can see already that our newly added component has changed orientation. So it's no longer being modeled sort of lengthwise left to right. It's switched orientation. It's now being modeled top to bottom. And you can see that it's already been duplicated as well. So I've created this one basic shaft shape here, but it's been duplicated at the top as well to show us that it's a repeated system based on a per planet basis. So if you've got 3 planets, it will repeat 3 times and so on. And if I move that, you can see how those two interact. Now I can change the orientation to make the modeling a little bit easier by clicking on the component that's been modeled in the other orientation and hitting this button up here, which is Base View on Selected Part. And then I'm just going to modify that shaft shape, remembering that this is the stub shaft, not the pin shaft. So this is the one that's going to be overridden by the FE eventually. So its geometry doesn't specifically matter, but it does need to act as that connection point for the clearance bearing, which is going to be sat around here. Okay, so perhaps something like that. And you can see how that's been repeated around the system. If I want to sort of view this as I'm building it, I can make it so this outside casing is not overly visible, so I can see what I'm modeling inside. So if I click on the differential shaft component, right click on the assembly view, I've got to hide part in 3D. That will just allow me to see the internals. Okay, now from the stub shaft, and I might want to make it a little bit larger so I can select it from, so it's not hidden behind the carrier shaft the whole time. Now what I'm going to do next is actually start connecting components to create our pin assembly. And just to reiterate, this is going to be connected to the stub shaft, not the carrier shaft. So I can start off with a bearing or some form of connection in the middle here, which is going to actually connect to the bearing to the planet pin. So just to show you what I mean, if I attach a concept bearing here, I could change it to a clearance bearing if I wished, or I could have it as a bond. It depends on my particular system. And that is basically acting now as the connection point between the carrier shaft and by extension the stub shaft, and the actual pin itself. So for going back to our complete model, that is acting as the connection point between where our pin sits in our differential housing. Next, I can model the pin shaft. So again, I'm just going to drag and drop shaft. Another component to connect to what will be my planet blank. So I'll just stick it as a concept bearing again, but it could be a clearance bearing or a bond or whatever it is in reality in your system. And then on top of there, I'll create another, which is my planet blank. Now you will notice that you can only modify the actual geometry on one side of this, and it just so happens that the reference drawing I have is not, the internals I want to model are not on the same side as the one I can adjust. That's just a quirk of the particular model I'm making, but it is only possible to adjust one side, and then that, as I mentioned, is just repeated for all of the pins within your system. Now, I won't make this shape exactly. I'll just try and keep it fairly simple. Okay, so there is our planet blank, which is now mounted on our pin shaft, in this case by a concept bearing, but I could very easily select that and change it to a radial clearance bearing if I want it just to be sat on top of that shaft. Now, one of the primary reasons for having that stub shaft is to model the clearance here, especially if this is free to move axially. So if I start off with a concept bearing, I'll put that on there. Now if I select that and go down to model, I can change that modeling type to an axial clearance bearing. But before I do this, I want to make you aware of one of the main problems that people experience, and I'm hoping I'll be able to replicate this fairly simply. Okay, there we go. So I've brought that bearing in there and connected both sides to the different shafts, thinking, okay, well that's a connection between those two, and it might look a little bit clearer than that. So something like this, for example, that has the same problem. So if I select it, you can see it's got this error saying that the component is axially mounted off the end of the shaft. However, visually it looks okay. And the reason it's doing this is because, again, it's an orientation thing. When you've got a concept bearing, which is what this is and what is often by default modeled for these systems, it's looking for a connection on the top and the bottom, when in reality this connection is looking from left to right. So all you need to do to resolve a problem like this, if you see it, or at least the first thing to check, is to just make sure that these are specified as axial clearance bearings, because then it expects the connections on the left and right hand side rather than the outer and the inner diameter. So that's just done under the model section and change from concept to axial clearance. So I'll do that with our model as well. from concept to axial clearance. Now you also want to make sure that they are connected to the sides you expect. You want to make sure that this side is actually connected to this component and this side is connected to this component. It might sound fairly rudimentary, but it's very easy to get those the wrong way around accidentally, and then your model won't be able to converge and see those as a connection. So you can do this just by selecting the axial clearance bearing, and where it says left and right, you can select those, and I can see that my left connection is connected to the left component and my right is connected to the right. So I'm happy with how that is modeled. Okay, the next thing I'm going to do is to actually create our gear set, our differential gear set. So if I go to add gear sets, differential, and then I have a few options. I have a straight bevel differential, a spiral bevel, or a zero bevel differential. In this case, I'm going to just import a gear set from my existing model, just because I know it fits this particular system, so it saves us messing around with this. To import gear set designs from another MASTA model, I can just go right click and import, and that will then allow me to import any geometry from an existing model. So if we're reusing a differential gear set, for example, or reusing any shaft designs or anything, we could just import them from another model. My mistake there, choosing a model with a fairly large FE component, so it took a moment. Okay, so I want this differential bevel unit. Click OK, and then it will import those in for us. So in terms of actually importing or inputting geometry for these, it's much the same as any bevel or hypoid within MASTA. So it's not MASTA's main strength to do bevels and hypoids, but we can put those gears into the system. We can model them based on defined geometry and perform some ratings on them. So I won't go through all the available options, but for your specified design method, you'll have properties available to you which will allow you to put or fully detail the differential gears suitable for your system. Okay, so what I'm going to do is connect my planet to the planet blank. So it recognizes that we've created a planet there. It knows that it needs to repeat that planet gear within that system as many times as we specify. So you can see it's appeared and connected to both sides now. And because we're going through the differential gear set here, that's actually changing the orientation back again. So when we start modeling other components, so the sun left and right, blank for example, that's now going to be in the other orientation again. So the same orientation as the housing is here. Okay, so I can start doing that now. So I'm just going to make a very basic shape here, not to spend too long trying to replicate the exact shape. And I'll duplicate that. Go to the right side. Okay, so from here the process is fairly simple. It's just connecting a few components together at this point. So the first thing we might want is some kind of support between the actual half shaft itself and the bearing casing. Depending on your system, that could be a bearing, it could be just a clearance that we need to define, but it's best to have something in there. So I'll just put in a couple of clearance bearings to keep it nice and simple for us. A couple of concept bearings to keep it simple. And then a couple of axial clearance bearings at these two locations here. And again, that's just controlling or constraining the axial motion of that system, because there will be some load coming through the differential here. It's just if it gets pushed in that direction, we want it to know that the load will be transferred to the differential casing in this case. So again, I want to make sure that I connect these correctly. So I'll start off with a concept bearing and switch that to an axial clearance bearing. I've got a property that will let me change its contact diameter. And again, I just want to make sure that's connected to both sides and that the left and right connections are the correct way around. So it looks like it's correct in this sense. I've not connected my right hand side yet, and my left side is connected to this one here. Okay, and I'm just going to duplicate that one. And you'll notice when I connect an axial clearance bearing directly to a shaft, it gives me the option to select which side is being connected. So it makes it even clearer for us. So I'll say right hand side for that one. If I wanted to switch it, so if I got it wrong, for example, if I select on the axial clearance bearing, there's an option on the tab along the bottom here, which is swap left and right. So if you've got it the wrong way around, it means you just don't need to disconnect everything. You can just click that to choose which side has been connected. Okay, then a couple of power loads just to define our output locations. And I'll just go ahead and very quickly create a load case and see if this has actually worked. It's quite a complex little system in reality, so there's a chance I might have done something slightly askew, so we'll give that a go. So I'll give it an input torque and speed, and then a low speed on one of the outputs. and then run, see if it's able to calculate. Okay, so this is another problem that you may experience. It's the same error as we saw on one of the bearings. So the component is axially mounted off the end of the shaft it's mounted on. And often case, this is just how you've modelled the blank that the gear is mounted on. And it is just a case usually of just playing around with the dimensions there until it connects the two. There we go. So all I did was a slight change to the actual shaft dimensions there. It just confirms to the unit that it is actually connected to the component it thinks it's connected to. So if you do see that error on one of your gear sets, just have a play around with the shaft dimensions and just make sure everything's looks like it's connecting in your 2D view. There's no gaps, for example. So that's able to calculate a resulting output speed and torque. And if I quickly go to my power flow, we can see that in operation. Okay, so there is another problem that sometimes comes up that didn't actually occur in the creation of this model. And I think I do have a preset model which has it. And sometimes when you are trying to connect all of the units together, you will see an error in terms of it's not able to split an assembly or some kind of error along those lines. So this is the problem I'm referring to. So there's a couple of things which are not connected here. So we don't have a connection between our right sun gear and the right half shaft, and we don't have a connection between the planet gear and the planet carrier shaft. And trying to connect either one of those results in a kind of failure. So one says it just can't split the two assemblies and it gives you a problem connection, and we should get a very similar message on the other problem one as well. So yeah, it's just saying it couldn't split the assemblies. And the general fix for this is really to just connect components in a slightly different way. And the way in which it goes about it might not really make logical sense, but just the way in which the components, the order in which the components are connected can seem to throw MASTA off sometimes. So if you come across this issue, just try and reconnect it in a slightly different way. So for example, if I go for this one it said was a problem connection, and I will remove that one to begin with. Now I'm going to start off with a connection to my planet blank here. So the planet gear, I'm going to connect that to my planet blank. So I know that's now connected. I'm now going to try and connect this one to my left half shaft, which has worked. And then I imagine this right one will probably still have that problem. Yeah. But now hopefully, if I try and reconnect this one in a slightly different way, so I'm going to try just completely isolating it to begin with and then connecting it to the gear first, hopefully that will now resolve our little problem. And there we go. So you can see that there's no errors now, so it would tell me if there was any connections missing. I grant you that the logic behind that is a little bit questionable, but it's a good way of trying to go about a solution rather than just getting frustrated with this message that keeps popping up. Just try and connect components in a different way. If you do still have problems with that and you really are struggling to find that solution, then of course you can message us and we'll be happy to help out in our support. Okay, so the last thing I want to show you is the addition of the FE really quickly. I won't go through it in a great amount of detail. Obviously, there's plenty of tutorial videos on adding FE. The main reason I want to reiterate this point is this stub shaft section I keep going on about. So in here, in this system, we have asymmetry in the differential carrier, so therefore it's a prime candidate for FE component replacement. And we also have this little stub shaft component here, which we've used to create our assembly and connect everything together. But we need that to be replaced, and the housing to be replaced by one component, so we don't count any additional masses or stiffnesses, and so we're confident in our system. And we can replace both the carrier and the differential stub shaft with one FE component. And that's what's happened in this system here. So I won't go through the process, but all we've done is brought in our FE component. And when I've actually gone to replace the shafts, I've also replaced, as well as the actual carrier shaft itself, I've replaced the carrier stub shaft as well. So if I start selecting and deselecting that, you can see the changes that makes. It selects and deselects the stub shaft. All of those selected shafts are now replaced by that one FE component. And it means that our components that are on the different axes can now be connected directly to that carrier shaft component. So for this axial clearance bearing here, for example, the left will be connected to here, and the right, because it's now replaced with an FE, will be connected directly to this whole replaced assembly. So for example, if I select these components here, go to connections, modify that search region, you can see that that's now connecting to it's connecting to nodes on my FE. So it's actually grabbing nodes on that FE, irrespective of the orientation of the MASTA component that was modeled. So hopefully that clarifies why that's an important thing to consider. Okay. So I think that covers about everything that I wanted to tell you in terms of modeling differentials. Hopefully it helps with your own modeling processes. As I mentioned, this video will be uploaded both in webinar form and as a tutorial video form fairly shortly. So if you need to review it again, you're more than welcome to. And if you do struggle, including with those tips that I've mentioned, you do know, of course, how you can contact our support team, and we'll be happy to help you out. Okay, so the next session like this will be in around about 2 weeks' time, where we'll be having another workshop. Details will be coming out shortly for those, and it'll be a much longer session. I think this time it might actually be FE in MASTA, so if you're interested in that, please keep a lookout in your emails or on the SMT website, where you'll be able to sign up for that for free. But apart from that, thank you very much for your attendance today and your attention. If you have any residual questions, please let me know in the box on the right hand side. Type them in there, I'll try and answer them. If not, if you're happy, then thank you for your attention, and we'll speak to you at the next training session.